Okay, everybody, today I just want to do a quick lesson on 6-5. So we're talking about basically stoichiometry with electrons. Um, we're going to talk about plating metals onto other metals, just basically how it's done, but really the calculations we need to know. So we need to learn something about electricity. So we're going to learn about current, and we're going to learn about Faraday's constant. Okay, we need both of those things to do the type of stoichiometry we're going to do today. All right, so that's the main thing. All right, so and if you understand this, then basically you understand 6-5, and we're good to go. All right, so let's jump into it. All right, so the first thing is. You might want to go over these notes here. The electro stoic review. It tells you what Faraday's constant is, what an amp is, our measurement of current, how to use them to convert from one thing to another thing. And really, remember, stoichiometry is basically just dimensional analysis. So these are kind of the setups we're going to learn today. And we just have to know a little bit about electricity to do it. All right. So make sure you kind of go over this, and then maybe that'll make sense. What we talk about today will make sense. So again, today is just kind of a quick overview. So let's go to the lesson notes, and let's pause for a second to make fun of the chemistry teacher who can't spell. I understand that. I understand that plating is with one T, so this should be metal plating with one T. It was early when I wrote the notes, so you can make fun of the chemistry teacher, but just remember I'm also a professor of logic at the University of Science, so don't mess with me. All right, so let's get back to it. So electrostoic is just stoichiometry with electrons, and metal plating is basically you're taking metal ions and you're reducing them back to their normal neutral metal state onto a piece of another metal, right? So we have metal ions, let's say zinc 2 plus, and if we add 2 electrons to it, we'll get solid zinc. And what we do is take our piece of metal that we want to coat or plate with the other metal. We dip it into a solution that contains the ions of the metal we want to plate it, and then we have to run electricity, which is electrons, through the piece of metal, and then the zinc or the metal ions that we want to plate will be reduced right at the surface of the metal and plate onto it and coat it with the metal. So kind of show you that. But if you've ever heard of galvanizing, galvanizing is a specific type of metal plating, and it's just coating your piece of metal with zinc. And the reason why you would do that is, let's say you took a piece of steel, which is iron and carbon, but you don't want the iron to rust, right? Because if the iron rusts, then the integrity of the steel, weakens, right? So what you do is you galvanize it, you coat it with zinc, and zinc is kind of the sacrificial metal. So instead of the iron getting oxidized, it'll be your zinc that gets oxidized, right? So the steel, the core of that piece of metal will stay strong because we're not going to oxidize any of the iron. We're only going to oxidize the metal coating that we put on it, and a lot of times zinc is the one to do it. All right, so essentially this is kind of a very simple version, but let's take our piece of iron, and if we wanted to coat it in zinc, we'd have to have a solution of zinc ions, right? And we would dip our iron into the solution, and we would hook our iron up to a source of electrons. Electrons would flow down through the iron and reduce the zinc from zinc 2 plus to solid zinc right at the surface of the metal, and we would start to coat our iron with zinc. Okay, so that's the whole idea. All right, so the zinc gets reduced, and we know that it takes 2 electrons to get 1 zinc, So 2 moles of electrons will give you 1 mole of zinc, and we can coat our iron with zinc, and that means it's been galvanized, okay? And again, maybe you've heard that word galvanized before. Remember, we've been talking about galvanic cells. So galvanizing, galvanic cells, it's not a coincidence, right? All right, so let's keep going. All right, so the question is, hey, how much zinc gets added to the iron? Okay, well, here's a stoichiometry question, right? Here's a stoichiometry question. So to know how much zinc is going to be plated onto that piece of metal, right, we need to know how many electrons do we add. And if we look at the equation right up here, it says, hey, for every 2 moles of electrons, I get 1 mole of zinc. So let's say if I know I added 2 moles of electrons to the solution, I know I get 1 mole of zinc, and then if I multiply by the molar mass of zinc, that would tell me how many grams of zinc I got, right? So that's the idea. We need to know how many electrons we're adding, right? So if you ever ask this question, like how much metal are you going to get, you need to know how many electrons you're adding, but also the really important thing, and I'll show you why this matters here in a second, but you need to know the charge of the ion that you're reducing, because you need to know this ratio. How many electrons does it take to get one of the neutral pieces of metal? So if my metal ion is 2+, it's going to take 2 electrons. But what if it was 4+? If it was 4+, it would take 4 electrons, and the ratio would be 1 to 4. Because we need to know that ratio, because we're going to use that ratio. That's our ratio in our stoichiometry, right? We want to convert moles of electrons to moles of zinc, right? Basically, all right? All right, so we need to know how many moles of zinc, and as soon as we can figure out how many moles of electrons we added, and if we know how many moles of electrons we added, we can figure out how many moles of zinc were produced, because we know the ratio 1 to 2, and then we can, get our mass of zinc produced, okay? So the things we need to know to figure out how many electrons we added to the solution to reduce, a certain amount of zinc atoms, is we need to know the current, okay, of the electricity we added, all right? So current is measured in what we call amps, okay? If we know the current and we know the time that we allowed the current to run, then we can figure out charge, and then we can figure out moles of electrons. So I'm going to show you how. So first of all, current is measured in what we call amperes. Sometimes it's short for amps, okay? But the symbol of it is I, and this is on your formula sheet, and it tells you that I equals C over S. So what that is current, or amps, is the same thing as coulombs per second. So if you're given an amount of amps, you're told how many coulombs of charge are passed through the wire every second, right? So let's say you had 15 amps. That means it's really 15 coulombs for every 1 second. So the way to interpret that is 15 coulombs of charge for every 1 second, right? So you need to know your amps, 12 amps, 15 amps, 30 amps, whatever, okay? And then what amps will be, it will be our conversion to convert either the total amount of time we ran the current into total coulombs of charge, or coulombs of charge to time. So amps is going to be our conversion factor to convert seconds to coulombs or coulombs to second, all right? But again, remember, our goal is to get moles of electrons. So now we have to bring in what we call Faraday's constant, okay? So on your formula sheet, I forget it off the top of my head, and that's why it's on the formula sheet, but on the formula sheet, you have the charge of a single electron. It's a very small number. It's like 10 to the negative 19, okay? That's 1 electron is that many coulombs. So Faraday figured out how many coulombs a mole of electrons has, and basically if you just take the number that's on your formula sheet where it says, hey, this is the charge of 1 electron, if you multiply that by Avogadro's number, that would end up being Faraday's constant, right? So Faraday's constant, and this value is also on your formula sheet. It tells you that there's 96,485 coulombs for every 1 mole of electrons. So think of it as an equality. You could say 1 mole of electrons for every 96,485 coulombs, or 96,485 coulombs for every 1 mole of electrons. And so Faraday's constant is our conversion factor to take total coulombs and convert it to moles of electrons, or moles of electrons back to coulombs, okay? So amps will get us, so if we know amps and we know how long we ran the current for, if we do seconds times amps, that'll give us coulombs. Coulombs divided by Faraday's constant will give us moles of electrons. And once we have moles of electrons, then it's just stoichiometry as usual. We go to our mole ratio and our balanced redox reaction, or in this case, our balanced half reduction reaction, and we do the stoichiometry, all right? So we got Faraday's constant, again, it's on our formula sheet, and amps would be something that's given to us in the question, all right? So let's actually try to do a calculation here. So it says, what mass of zinc will be added to iron if 20 amp current runs for 15 minutes? And we got to remind ourselves that zinc is a 2+ ion. So our source of solid zinc is coming from zinc 2+, and we know it takes 2 moles of electrons to get 1 mole of zinc. All right, so what we got to do is get 15 minutes and 20 amps, and we got to get that to moles of electrons. Once I get moles of electrons, times 1/2 will give me moles of zinc, and then times the molar mass of zinc will give me the mass of zinc. All right, so here's the essential setup. All right, so we would take our 15 minutes, and we got to convert it to seconds because amps is coulombs per second. So 15 minutes times 60 will give us how many seconds? Seconds times amps. Remember, amps is coulombs per second. That'll cancel out seconds and give us coulombs. Coulombs divided by Faraday's constant will give us moles of electrons. Our mole ratio for this reaction was 1 mole of zinc for every 2 moles of electrons. And I ran out of room, so I went down here. Then what I would do is take my moles of zinc and I would multiply by the molar mass of zinc, find that on the periodic table, and we would get how many grams. So if we ran that current for 15 minutes, we would expect to get around 6.1 grams of zinc onto our metal, okay? All right. And sometimes we might go back the other way. So here, we want to know how long. So notice, like in this question, we started with the total time and we got to mass. So in this question, we're going to kind of do the opposite. We're starting with the mass of metal that's going to be plated, and we want to know how long we have to run the current for. So basically just the reverse, all right? So it says how long, in hours they want, would be required to produce 110 grams of chromium. And notice that our source of chromium is chromium 3 nitrate if you have a 30 amp current, okay? So the first thing you want to know is what's going to be our mole ratio of solid metal to moles of electrons. So notice it's a different ratio. This one is 1:3, and the reason why it takes 3 electrons to produce 1 mole of chromium is because the chromium, our source of chromium, is chromium 3+. So again, if you want to plate metal onto metal, right, you got to reduce the metal ion all the way to its neutral state. So yeah, you can reduce chromium 3+ to chromium 2+, but that ion would just stay in solution. To plate it onto the metal, you have to reduce it all the way down to its neutral state. So because we have chromium 3+, now our mole ratio is going to be 1 mole of chromium for every 3 moles of electrons. Or in this case, we're going to do 3 moles of electrons for every 1 mole of chromium. So let's do the setup. So we would take our 110 grams of chromium, figure out how many moles that is, and we know it takes 3 moles of electrons to reduce 1 mole of chromium, right? So divide by the molar mass of chromium, moles of chromium, times our mole ratio to get moles of electrons. Then moles of electrons times Faraday's constant will cancel out moles of electrons and give us coulombs. Coulombs divided by amps will give us seconds, right? Because it's 30 coulombs for every 1 second, or 1 second for every 30 coulombs. So coulombs divided by amps is going to give us our seconds. And we wanted to know hours, so now seconds to minutes and minutes to hours. And if we do all the math, we end up with about 5.67 hours. So if we run our current through the solution, as long as we have enough chromium 3+ ions, and we weren't, told to think otherwise. So, electrons would be our limiting reactant here. So as long as we have enough chromium ions in solution, if we run that current for 5.67 hours, we should get around 110 grams of chromium produced, right? Okay. So real quick, I just want to show you, where this, can come up on the AP exam. And this type of question did come up on last year's AP exam. So we're going to do this in class, the whole thing, but I just want to show you the second part, okay, of the question. So this is an electrolytic cell. So this is a voltage source is being applied to this cell so that it goes in the non-spontaneous direction. So you can read through that question, but I just want to go down to here. If the current in the cell is kept at a constant 5 amps, how many seconds does it take to produce 2 grams of magnesium liquid? All right. So if we go here, our source of magnesium liquid, right, is magnesium 2+. So it's going to take 2 moles of electrons to completely reduce magnesium 2+ to neutral magnesium liquid. All right. And so this is going to be the exact same setup we did, but we're only going to seconds. We don't have to go to hours. But we're going to start with our grams of magnesium, and we're going to convert it to moles of magnesium by dividing by the molar mass. Then it's going to take 2 moles of electrons for every 1 mole of magnesium, because magnesium is a 2+ ion. And then times Faraday's constant divided by amps, and that would give me seconds. So let me show you the setup. Okay. So we would take our 2 grams of magnesium divided by the molar mass of magnesium. That would give us how many moles of magnesium we want to produce. We got to recognize that, again, our source of magnesium ions is 2+. So it takes 2 moles of electrons to completely reduce it. And then if we take our moles of electrons and we multiply by Faraday's constant, that'll give us total coulombs. And then coulombs divided by our amps will give us our total seconds. So there's our seconds. 3,180 seconds. If we divide it by 60, that would give us our minutes. If we divide it by 60 again, that would give us our hours, that kind of thing. So, but here, just a simple electrostoic problem, not very difficult. The only thing you really needed to know was, hey, it was magnesium 2+. Okay, so you get that right ratio. But everything else is just dimensional analysis. But you got to know what the things mean, right? So you had to know that amps really meant this: 5 coulombs for every 1 second, or 1 second for every 5 coulombs, right? That's what we needed to know. All right, so if we had no idea, if we've never seen amps before, that's gonna be a tough one. All right, so that is just kind of our quick and dirty, just, hey, this is what you need to know about electrostoic. And basically that's unit 6. I wish we could spend more time on it. It's just we're coming down to the wire. We still got unit 7, so you got all the information that you need to attack the unit 6 assessment. So go practice that. And if you understand it, you're in good shape. Those are the types of questions you'll see on the AP exam and the final exam. So just getting you set for that stuff. All right, so that's it. Hope you enjoyed today's lesson on electrostoic. And have a good one.